Let's see an example of using the MH sampler to draw a sample from the Rayleigh distribution. So the Rayleigh distribution has probability density given by fx that's equal to x divided by sigma squared times the exponent of negative x squared divided by 2 times sigma squared. The x in this case is the random variable we want to draw, and that's supported on values greater than or equal to 0. There's only one parameter in this distribution, and that's our sigma. And sigma is restricted to be greater than 0. What we're going to do is to use the Metropolis-Hastings algorithm to generate a sample of x's that come from this distribution fx. In order to do this, we will first generate an initial value, x0, which comes from the chi-square distribution with 1 degree of freedom. You can see that this choice of the chi-square distribution is quite arbitrary. In practice, you can either randomly sample the first value, you can choose something close to the mode, or you can just fix it to any arbitrary value within the support of this particular distribution. Followed by generating the initial sample for each t greater than or equal to 0, given xt, which is the tth iteration of x, we will first generate a y from the proposal distribution, that is the chi-square distribution with xt degrees of freedom. You can see that in this case, we chose the chi-square distribution as the proposal distribution, and depending on the last xt, we will use different kinds of degrees of freedoms when we generate the y. Without loss of generality, let us implement this MH sampler for the Rayleigh distribution with sigma equals 4. You can find the code for this week's examples, and the examples week 11 are markdown file. Okay, so instead of going directly into the code, let's try to recap the MH sampler and see what it translates to in this particular example. As we have mentioned, step 1 will be generating the initial x0 from the chi-square distribution with 1 degree of freedom. For step 2, for each t from 0 to n, we will first generate a y from the chi-square distribution with xt degrees of freedom. In other words, the chi-square with xt degrees of freedom is our proposal distribution. Next, we will generate u from the standard uniform distribution between 0 and 1. We will then compute this ratio, g of xt given y times fy divided by g of y given xt times fxt, where f over here in this ratio is the target density. So in this case, it's the Rayleigh density with sigma equals 4, evaluated at y and evaluated at xt. And g conditioning on xt, which is in the denominator, and g conditioning on y, which is in the numerator, are the chi-square distribution densities with xt degrees of freedom and y degrees of freedom, respectively. Then we will perform the test and see whether we will decide to reject or accept. If the u we generated in this step is less than or equal to this ratio, we will accept this sample and set the next x value, xt plus 1, to be equal to y. Otherwise, if u is greater than this guy, we will set the xt plus 1 to be equal to the last one, which is xt. So to implement this code, let's first create a function for the Rayleigh density. So this function f is the Rayleigh density. It takes value x, which is the random variable's value, and also the sigma parameter, which in our case is equal to 4. So for x's that is outside of the range, so for x's that are negative, the density will be equal to 0. And if sigma is not positive, we will stop this and say this is not a valid sigma. Otherwise, this function will return a f of x, where that is the Rayleigh density. So this is given by x divided by sigma squared times the exponent of this guy. So essentially the Rayleigh density. So now let's start to generate the xt's for t equals 0, 1, 2, all the way up to 9999. So you can see we are doing this for a total of n equals 10,000 iterations. We will first create empty vectors or zero vectors of length 10,000 to store our x's, which are our metropolis Hastings samples, and the acceptance or rejection decisions, whether at each iteration we accepted the sample from the proposal or we rejected the sample from the proposal. The first entry of x, our x0, in this case x1, is equal to a random sample that's generated from the chi-square distribution with 1 degree of freedom. And for each subsequent case, we will first generate a y from the chi-square distribution with degrees of freedom equal to the last iteration of x. And then we will calculate the probability of acceptance. And that's given by gxt given y, which is the chi-square density of xt when this is a chi-square distribution with y degrees of freedom, times fy, which is the Rayleigh density of y, divided by g of y given xt, that is the chi-square density evaluated at y when the degrees of freedom is equal to the last xt, times, I'm overflowing over here, but the last one is just fxt, which is the Rayleigh density evaluated at the last xt. So this gives us the probability of acceptance. If the p is greater than or equal to our uniform sample, so our uniform 1, then we will accept and set the next x, which is xt plus 1, to be equal to this y. We will also set the accept entry, which is the vector of length 10,000 that stores whether at each iteration we accept or reject, to be equal to 1, indicating that we have accepted this particular y sample. Otherwise, we reject this sample and we set the next xt plus 1 to be equal to the current xt. So this will iterate for a total of 9,999 replications, and we will end up with the vector x that contains the 10,000 draws, including the initial draw, which is from the chi-square distribution with 1 degree of freedom. So let's take a look at a few things. The first is the acceptance rate, and this is given by the mean of the accept vector. So the accept vector is either 1 or 0, indicating for that particular iteration whether the y was accepted. If we take the mean of it, it gives us the percentage of samples that were accepted. And in this case, this is quite close to 0.6, meaning that about 60% of the draws from the proposal distribution were accepted. Let's also plot the values of the draws. In other words, let's plot the Markov chain. What we're going to do is on the x-axis, we will plot the chain index. It is also okay if you omit the x-axis in this case and just do plot x. And the y-axis is the corresponding x value for each of the iterations. So this tells us as the iteration number increases, how does the draws of x from using the metropolis Hastings sampler progress? The earlier plot might be a little bit hard to see, so let's zoom in a little bit and look at the last 1,000 iterations. This is given by the last 1000 entries of the X vector. And you can see that in this case, this is the chain. And around the center of this distribution, so you can see that the X draws have mean, or they're centered kind of around, I think this is something around 6. And you can see that in every iteration, there are some fluctuations. However, if you zoom in a little bit and look closer, you can see that at some of the times, the next iteration's value will be equal to the value from the previous iteration. And that is the case where we have rejected a proposal draw and we have set the next xt plus 1 to be equal to the current xt. So let's take a look at the histograms. And when we look at the histogram, what I want to show you is first a histogram of the first 1000 iterations from of the x's. That's our MH draws. And I have also imposed the Rayleigh sigma equals 4 density on the top, so you can compare the two. So here's the plot or the histogram for the first 1000 entries of X. So our initial one up to the 1000th iteration. And in this case, you can see that it seems like the empirical density of the x's are quite close to the theoretical density of the Rayleigh distribution, but there are some minor discrepancies, for example, over here. Let's also take a look at the histogram. Okay, so maybe due to randomness, this is not a very good example. But we can also look at the histogram of the X draws with the first 2000 ones tossed away. So you can see that in this case, the draws are also quite close, and actually very close to the Rayleigh density. So with these samples, sorry, just to add one more thing. My intention was actually to show you that when you're at the beginning of the chain, the values of your draws can actually be a little bit far away from the Rayleigh density. But for maybe for this case, it wasn't really that far away. So that chain might have converged really fast. But in general, you will expect that at the very beginning for the first a few or the first set of x's, they will be they haven't yet converged to the stationary distribution, and in that case you might want to toss away the initial samples when you try to calculate some for example, to calculate some Monte Carlo estimates using the samples that you have drawn. We will talk more about this later on. So let's take a look at the Monte Carlo estimates, or the point estimates of some parameters. So with these samples that we have drawn from this Rayleigh density, we can estimate the expectation of a function h with respect to the density f. By definition, this is given by EF of hx, which is equal to the integral of hx times the density fx dx. Under some regularity conditions, we can use the draws from the chain to construct a consistent estimator for the expectation of hx. So let's denote it by theta hat, which is the familiar Monte Carlo estimator you have seen in earlier weeks. So this is the sample mean of the hx size across a total of m iterations. In this case, the xi's are our draws from the Wachowski-Hastings Markov chain. So I have previously mentioned a little bit about this. So it is common to eliminate draws x1 all the way up to xb from this calculation of the Monte Carlo estimate. So here b is a constant, so a time point that is large enough to assume that the chain is close to its stationary distribution beyond B. In other words, all the x's after B are assumed to be close enough to the stationary distribution or the target distribution that we want to draw samples from. So this initial segment between 1 and B, or the x's, is called the burn-in phase. We want to toss away the burn-ins when we calculate the Monte Carlo estimator. In this way, we have theta hat, which is equal to 1 divided by m minus b, and then the sum from b plus 1 to m of h evaluated at the xi samples. Let us use this idea to estimate the expectation and the variance of x in the case of Rayleigh distribution with sigma equals 4. We know that the theoretical mean and the variance for the Rayleigh distribution are given as follows. So we will try to see whether these are close to the Monte Carlo estimates that we get when we simulated the chain using Metropolis Hastings. In this case, we have a total of, I think earlier we assumed that n is equal to 10,000. So we will treat the first 5,000 iterations as our burn-in and just use the last 5,000 iterations to calculate the theta hat. Let's first compute the mean Monte Carlo estimate. And this is denoted by mu hat, which is simply the mean of the x's from the 5,001th iteration all the way up to the last iteration. And that gives us something around 5.11. The true value of the mean, which is given by sigma 4 times the square root of pi divided by 2, is equal to 5.01. So you can see that they are not too far away. Similarly, we can look at the variance estimate. We know that the variance is equal to the expectation of x squared minus the expectation of x, which is the mu of x squared. So the variance can be estimated by taking the mean, the sample mean of x squared across the last 5,000 iterations, minus mu hat, which is the mean of the x's in the 5,000 iterations squared. That gives us something around 6.68, which is also quite close to the theoretical mean of 6.87.